So, all right, so everyone, let's get started. So the lecture today will be the third part of the linear algebra review. We'll mostly be talking about special properties of square matrices, and so most of the stuff we'll talk about in the lecture today will be laying definitions, and so foundations we'll need later in class, and a lot of the concepts like some things like how are we going to compute this thing, or what does this really mean, are things we're going to have more lectures later in the semester about. And so most of the things about square matrices, we're not going to talk about all of them, but about properties that will be coming up when we have problems from data analysis. So there's a whole bunch of deep stuff you can go in here in linear algebra, and we aren't going to go into all that. We're going to go into the parts that the definitions that will make life easier for us kind of later in the semester. So just where we are on the schedule. Yeah, so we're finishing up the linear algebra review. Quiz number 2 is happening today as well, right? So we will stop at by 10:35. I'm kind of hopeful we will kind of finish up before then, and then you can ask me questions about stuff that might be on the quiz until then, but we'll see how it goes. And then I guess homework 2 is due on Tuesday next week. I guess starting to get a little bit busier in the office hours. Kind of make sure not to wait till the very last minute, because often office hours are going to be extremely crowded on right before it's due. Okay, yeah. And then right, okay, so this is the last part of the probability or the review lecture. We'll basically have the material to start doing the types of data analysis, and we will start with linear regression, and this will take us through the fall break. Yeah, so we'll start with linear regression on Tuesday. So probably kind of some people have seen linear regression before, but we will hopefully kind of give a very clear first principles perspective of it, and also go into some more advanced versions, although not as much as you can get in some some later classes. Okay, so let's get into the material and see if we can get through everything kind of a little early, and then you can ask me questions about what's going to be on the quiz. Okay, so this lecture will mainly be about square matrices. Okay, and these is going to be a matrix, right? So it's it's going to be an uppercase letter. I'll tend to use things like M for square matrix here, and in this case, it's square if it's going to have the same number of rows as it's going to have columns, right? So this is one reason why it's called a square matrix, right? Is because remember this picture I drew about the rectangles of the matrices that might help you think about, what the multiplication of matrices was looking like. Well, in this case, kind of the number of rows and the number of the columns is going to be the same. So this rectangle is now going to be a square. All right, so there are a number of kind of special cases of square matrices that are going to so come up in data analysis. And so in the case of the rectangular matrices we talked about so earlier, we were thinking those were filled with observations. They were n rows and d columns. Every row was an observation, had d kind of properties, attributes that you are measuring. Square matrices usually come up as like an intermediate step inside of the analysis. Okay, and so these are going to be constructed, not directly observations of data, but constructed, and that's going to infer on them or kind of give them some special properties. So we're going to talk about special properties that these matrices can have. Kind of the most, I would say the most important kind of thing about square matrix is that, so for a square matrix, you can sometimes define an inverse, okay? And an inverse of a matrix, so would be like, so the inverse of so I usually write this as, so taking it to the power, so -1, right? And so the idea of this is if instead I had a scalar, so if I had a scalar alpha, right? And then if I took alpha to the -1, this is equal to 1, so divided by alpha, right? So, and so 1 divided by alpha, well, what am I doing here? I'm doing division by a scalar. The inverse of a matrix is like, is what you want to do if you're dividing by a matrix. Okay, we talked about addition and subtraction and multiplication. If I want to do division by a matrix, I need to multiply by its inverse. Okay, so I can do the inverse operation, and then I multiply by that matrix once it's been inverted, and so that'll be like the equivalent of like doing division. So okay, so that's the think of. So it's so it's kind of like dividing, and we'll need this when we want to kind of solve an equation. You know, sometimes you need to isolate something, and you're going to take something from the left-hand side, move it a coefficient to the right-hand side, and you do that by dividing that coefficient on both sides. With matrices, you multiply by the inverse on both sides. Okay, and the reason why this works is that if I have a square matrix and I multiply by its, I take its inverse, right? And I multiply by the same matrix again, right? So this is taking the inverse and then multiplying by it, right? This is going to be equal to the identity matrix, okay? And this is true on both sides. So I can also do m-1 inverse. Okay, this is also the identity. So the identity matrix is going to be matrix which is all ones on the diagonal and all zeros off of here, right? So it's a square matrix again. This is also going to be in d by d. Also going to be a d by d matrix. If it's the product of two square matrices, they're both d by d. The inverse is also going to be a d by d matrix. And so a d by d times a d by d is a d by d matrix. And this identity acts like the 1, right? If I were to, in my analogy with scalars, if I were to multiply any scalar times 1 over alpha, the answer is going to be 1 here. So this identity matrix acts like 1. If I multiply any matrix by the identity, I get back the same matrix. Okay, and so if I multiply any scalar by 1 or any vector or matrix by 1, I get back the same matrix. This is the sense in matrix multiplication. Right? So I can't. The tricky thing about the inverse and why we did addition and subtraction and multiplication earlier, those were simpler. You cannot always take the inverse of a matrix. Okay, so this is so you cannot always invert a matrix. Okay, so if you can, you say it's so invertible. All right, and so what properties do we need to have if it's invertible? You can, the matrix has to be square. You can only invert a square matrix. So there's something called a pseudo inverse. We'll maybe talk a little bit about later, or I'll just mention later in the semester. So you can kind of do something like an inverse of non-square matrices, but to really do a proper inverse with all the things you expect about division, it has to be square, and so it has to be full rank. So okay, so it has to be square matrix, has to be full rank. This means that the rank of M has to be equal to D. Okay, so full rank, remember that it means that the rank is equal to the minimum of the number of rows and the number of columns. Number of rows and number of columns is the same as D, so that means the rank has to be equal to D. And what this means is that every column or every row, right? Every row is independent, linearly independent of all of the other rows. All the rows are linearly independent, and all the columns are going to be linearly independent. So that has to be the case if it's invertible. Okay, so if I had kind of a duplicate of a row, or one row is a constant multiple of the other row, like it's twice one of the other rows, then it's not going to be invertible. Okay, if it's not square, it's not going to be invertible, and that means I can't really divide by that matrix. So if I have an equation where I want to isolate something by undoing a matrix multiplication, I can't always undo that operation. It's kind of algebraically, there's some stuff that's so complicated. So luckily in this class, more or less, we're only going to try and invert things that we construct in a way so they are invertible. If something is not invertible, you probably should not try to invert it, because it's going to be like numerically unstable. There'll be some stuff that'll come up with regression where we'll discuss, some more about this. So the most important thing is that if you want to do inversion, division by matrices, you do inversion, and these need to be square matrices. They have to be full rank. Okay. All right. I want to with square matrices. I'm going to talk about this very briefly. So with square matrices, you can talk about their eigenvalues and eigenvectors. If you take a linear algebra class, I hope you learn about this. It's not always taught in linear algebra. We will spend a fair amount of time in the dimensionality reduction part of the class talking about singular values and singular vectors, which are kind of analogs of these for square matrices, kind of like that. But I just want to mention them now. If you haven't seen them before, if you have a square matrix, okay, M, so this is in R, and so D by D, then if you can write an equation where you have M, okay, times a vector and you get back a scalar times a vector. Okay, so then let's see. So this v, which appears on both sides of the equation, this is known as value. Okay, and this lambda. So oh no, hold on, I mixed this up. Said the wrong thing. This is known as an eigenvector. Right, so V is going to be an element of RD, and then so lambda is value, and it's going to be this is in R, so this is going to be a scalar. Okay, so this is a very kind of special equation that might seem strange. I've got a D by D matrix M, I'm multiplying by vector, and I'm getting back a scaled version of the same vector. Okay, this is unusual. If I don't have a square matrix, right, and I multiply by a vector, I'm going to get back a vector so its dimensionality is going to be different, right? If M was N by D, I can multiply by a D-dimensional vector, but I'm going to get back an N-dimensional vector. So it can't be a scale copy of it. So it has to be a square matrix for this to make sense. And what's special is that it's kind of pointed in the same direction here. Most times when you multiply by a vector by a matrix, that's kind of changing the vector in some strange way. It's stretching it and it's rotating it and doing stuff. This is a special case when I get back the same vector scaled by some of that. And so usually, you could, if I multiply a vector by 2, right? I take the vector and I multiply it by 2. I can do that on both sides of the equation, right? So if I put a 2 on both sides, it's okay, I can do that. But that kind of factors into the lambda. So usually you say that the norm, you consider the case when the norm of V is equal to 1. And then that gives meaning to the value of lambda. Then that gives it a specific value of lambda associated with that eigenvector. So the eigenvalue lambda is kind of defined typically, usually when you set the norm of V so equal to 1. All right. Okay. What's neat about these is that if I have a D by D, so matrix M, I can get a set of these eigenvectors and values. I'll get V1. These come together in pairs, right? So V1 and lambda 1, V2 and so lambda 2 up to VR, and so lambda R, where R is the rank. R is equal to the rank of M. You can kind of define these for larger values of the rank, but then it's the lambdas are going to be 0, and they're not totally specified. Okay, if it's full rank, then R is equal to D, and we're going to be concerned usually with square matrices, so which are going to be full rank. Okay. All right. So I can have up to D of these eigenvalues and vector pairs. These are mostly unique. The vectors are unique as long as the values are unique. There are weird cases with ties. Maybe we'll talk about that a bit. So later, there's also a little thing I kind of skipped over here, that these eigenvalues, there are some weird cases where these are not actually real. You can get things which are like imaginary here. Those are not going to come up in this class, so I'm just going to kind of ignore them. Okay. In particular, we want to define a nice class of square matrices called so-called positive, definite so matrices, okay? So this is a really nice class of the square matrices. So these are D by D, so matrices, and it's going to have D eigen vectors and so values, and each lambda I, its eigenvalues is real, and each lambda I is so strictly greater than 0. Okay, this will be the nice class of these of these square matrices. There are a lot of cool, neat properties about these, and we're gonna, if you have these, it's gonna make the operations easy. I can always take the inverse of these, because if it has D eigenvectors and values, its rank is going to be D. And so this is pretty much going to make our life easy. So also, these are kind of like squared some matrices. If I have a which is n by D, and say in this case, let's say n is greater than D, and the rank of A is equal to D, so it's full rank. Okay, and then I do A transpose times A is equal to M. This implies that M is going to be positive definite. Okay, so if I start with a data matrix that's recordings of data, and it's full rank, n is greater than D, right? And there's noise in my data, so it kind of everything is linearly independent of everything. Then I multiply it by itself, A transpose times A, to get a square matrix. This will be D by D. Then M is going to satisfy these properties. Okay, so this is what we're going to need. Then the eigenvalues and vectors of M are going to be real and positive, and everything it's going to be full rank, so I can take the inverse of it, and it'll have all these nice properties. All right, this is basically what you'll need to know about these. There's one variation I'll just mention here. A positive, semi-definite. Okay, so matrix M, I often will call PSD. So the matrix. So if this is in our D by D, it's still a square matrix. Let me write this a bit more clearly. D by D, so it's still a square matrix, and it's going to have D eigen values and so vectors. Each of the these eigenvalues are going to be reals, and each of the value is greater or so possibly equal to 0. Okay, so if some of them are exactly 0, then it's so positive, so semi-definite. This is a pretty nice situation. And if A is not full rank when I do this construction, I might get this sort of property instead. It's not going to be negative, and so things are still fairly nice, but this is going to be when things are, operations are more so unstable. Or as I approach this situation, will be unstable. So the positive semi-definite, the key difference here in particular is that it might, the eigenvalues might be equal to 0 instead of strictly greater than 0. So okay, right. So I don't think you need to know anything more about these now, but these will show up in our computation, and if we know properties about the positive definite matrices and that they are going to rise in this way, then we know that their eigenvalues and vectors are all so well defined and nicely behaved, and we can take the inverse of these matrices, right? So that's basically what you need to know. Okay, one more concept to cover, that is orthogonality. Okay, and this all defined for both vectors and matrices. Okay, so for vectors, P and Q, I can think about this. They're both going to be in RD, so d-dimensional vectors, and they are going to be orthogonal if and only if the inner product between P and Q is exactly equal to 0. Okay, if I view these in 2 dimensions, okay, I can think of a vector P as coming from the origin, and then a vector Q, if it's orthogonal, the dot product is going to be 0 if Q is at a right angle with P. Okay, so that there's this right angle. You may have seen in like a high school geometry class, you kind of draw this square kind of angle here. That's a 90-degree angle between them in so 2 dimensions. And this will correspond with their with the inner product of these being 0. Just to convince you, let me give you two examples. So just some simple examples, right? Let's say P is equal to 1, 0, so it's the x-axis, and Q is equal to 0, 1. Okay, so it's the y-axis here, right? Then P dot Q is going to be equal to 0 times 1 plus 1 times 0, which is 0, right? So if they're the x and the y-axis, then they're going to be orthogonal to each other. The axes are going to be orthogonal to each other. I'll give you a slightly more complicated example. Let's say P is equal to, let's do 1 and so minus 1. Okay, so let's draw this example here. P is going to be now 1 and minus 1. Now I'm going to make Q up here. So now Q is going to be 1 and 1. Okay, let's see if the dot product is 0. I have 1 times 1 plus minus 1 times 1, and this is equal to 1 minus 1, and that's 0 also. Okay, so these are also going to be orthogonal to each other. Okay. Yeah. Okay. So these pictures in 2 dimensions. So this applies in much higher dimensions as well. Right. So let's say that P is equal to, here's a more complicated example from the book, minus 1, 6, right? And Q is equal to 4, 5, 3, minus 7, 2. Okay, if I take the dot product of these 2 things, right, I can just take the coordinate y's and multiply them, right? So I'll get an 8 minus 3 times 5, this is minus 15. 4 times minus 3, this is going to be 12. Minus 1 times minus 7, this is going to be 7. And 6 times 2, this is going to be 12. What did I Oh, let's make this a -2 here. So this will be a -12. Okay. Okay, if I add up these things, the negative 2 parts gives me -27. And if I add 8 and 12 and 7, that's positive 27. So this is equal to 0. So these vectors, these high dimensional vectors, are going to be are also going to be they're going to be orthogonal to each other. And what this means is that they're living in a 5-dimensional space. But if I were to look at the projection, the 2-dimensional view that contain those vectors, the span of those vectors, the picture is going to look like this. They're going to be at a right angle with each other in kind of the 2-dimensional subspace that contains them in the origin. So they're going to be kind of exactly like this with respect to each other, but sitting in a higher dimensional space. So it's good to have this picture in your head, right? This 2-dimensional picture, because actually the span of the origin and the 2 vectors is always a 2-dimensional span. There's a 2-dimensional subspace that contains this data, and in that span, the picture looks like this. Okay, this is all right. Okay, so with orthogonality, it's the dot product of 0. These are right angles. We can think about matrix orthogonality as well. Okay, there are 2 types of, so what we'll think about is now if I have a vector V, and these will be a square, sorry, a matrix V, so this is an uppercase V, right? It's a square matrix. Actually, the first definition does not need this to be square, okay? And so if I want to think of having D, so columns, okay, we'll call this V1, V2 up to VD. If all VI and VJ in the space of the columns are orthogonal, right? This is uppercase V. Then I'm going to say that V is orthonormal. Okay, so this is a slightly weaker version of like orthogonality. Okay, so if I do, so I can multiply V by so I can do V transpose times V. Okay, what's the dimensionality of V transpose times V going to be? So it's going to be D by D, right? V transpose is D by N, so the N winds up in the middle here. So this is going to be D by D. And so then, so this is going to be equal to the identity matrix, okay? If I think about this, if I think about V transpose V, and I think about the ith j entry here, if you remember, this is going to be the inner product between VI, VI and VJ, okay? So what happens if I and J are not equal to each other? If I not equal to J, yep. Yeah, so then this is going to be 0. And what if they are equal to each other? Yeah, I forgot this property. If they're orthonormal, I also need the property that each VI has a norm of equal to 1. Yeah, if it's orthonormal, all the columns are orthogonal to each other and the norms of the columns are equal to 1. So they're all normalized, right? So now if I equals to J, now I have that VI right? So this is itself. This is going to be equal to the VI squared, the squared norm. Remember, the dot product of a matrix of a vector by itself is equal to its squared norm. And if it's normalized, so the norm was 1, so the square of the norm is also 1. All right, so that means the entries along the diagonal, right? So this would be I, right? This value is this value here. These are going to be 1s, and the values ij off the diagonal. So these values are all going to be 1, and this value is going to be 0, right? So that's for kind of all the values in here. And what I'm going to get is the identity matrix. Okay, but that's not true. I don't have that V transpose. I can also do this. This will be an n by n matrix, but this will not be equal to the identity because, well, I might not have the orthogonality property here. Okay, so and it's not going to be so full rank either. So so I might not have the identity here. So this, I kind of have something like, I can kind of do an inverse here of if it's an orthonormal matrix on one direction but not the other direction. Okay. Okay, so an orthonormal matrix is a step towards being orthogonal. So I'd say an orthogonal matrix, okay, is going to be a matrix which is square. So M is in R d by d, okay, and all rows are going to be are going to be orthogonal and so normalized, and all so in the same is true of the columns. All columns are also going to be orthogonal and so normalized. So so if it was going to be orthonormal, then I would just have this property, ortho so normal. But if it's orthogonal, then so then I have both. And so then it has to be a square matrix as well. And so the nice property I'm going to get now, if I have an actually I'm going to write this as a U here, then this matrix will have the property that U transpose U is going to be the identity, and also U transpose is also going to be equal to the identity. So if I do it in either directions, because this orthonormal property holds both for it and its transpose. Yep.
So if all the rows were orthogonal but not the columns, would that also be orthogonal?
You'd say that's the transpose of an orthonormal matrix. Typically, these are details in the terminology. Yeah. All right. One of the really nice things about orthogonal matrices, right? One of the nice properties I have, if I for any vector x in Rd, I'm going to have that if I look at the norm of x, right, and I'm going to compare it to the norm of U times x. Okay, it's the d by d matrix. So if I multiply x by this d by d matrix, I'm getting back a d by d. So vector again, and I want to compare the norms of these. it turns out these are going to be, so these have to be equal to each other. So it does not change the norm. It's true for any vector x. So if I take a vector and I look at its length, right, the distance from the origin, right, its length, and I multiply it by an orthogonal matrix, I'm not changing its length. Okay, so one useful way of thinking about this, right, so I've got a vector x, right, here, and I'm multiplying it by an orthogonal matrix. So I'm going to get another vector, say, maybe it's over here, ux, like this. They have the same length after doing this, okay? And it is useful to think about this as like rotating, right? All the vectors that have the same length, they form a circle around the origin in 2 dimensions, right? In higher dimensions, it's like a sphere around the origin, like a hypersphere. They all have the same length vectors, and so I'm rotating it. I'm rotating this vector. In higher dimensions, it's a rotation, and you can also do like some mirror flips. So depending on, if I change a sign someplace, it becomes a mirror flip in addition to a rotation, but it's basically a rotation of the vectors in the space. Okay, and we will see some kind of cool uses of this later in the semester. Again, this is a preview. It takes seeing this a few times for it to kind of sink in. So this is maybe one of your first times seeing this, but we'll see it again. All right, so this it's not changing the length of the vector, so it's kind of maintaining the length properties, but it's rotating the space. In fact, it's going to rotate all the vectors kind of in unison. It's the same rotation to any input vector. So if I did this again with another x prime, it's going to do the same sort of rotation here, and it's going to get ux prime. So it's the same sort of rotation in the space. Maybe the norms are different, so it's on a different circle, but it's rotating the same angle here. Yeah.
Is that like what transformation are you doing? Like where are you doing?
When I multiply, this is from x to the orthogonal matrix u times x. All right, so the first vector, the red thick line is x, and the green thick line is u times x, right? And so that's, right? So from x to u times x. Let me make u times x a bit more clear here. U times x, right? So if multiplying by an orthogonal matrix is kind of a rotation in the space. Okay. Okay, one last thing I will want to say is that, okay, so the columns u1 up to ud of u, so right, so where u is this orthogonal matrix. Okay, these form a what's called a orthogonal so basis. Okay, so that means that ui dot uj is equal to 0 for I not equal to for I not equal to j, and the norm of ui is equal to 1. Okay, so this is again, this property implies this kind of rotation interpretation. It's also so it means that if I take, and we will kind of go through this again, but if I have any vector and I multiply it, I do u times x. What I'm really doing is I'm so I can think of this as a new, as kind of a new vector, which is u1 dot x, u2 dot x, up to ud dot x, right? This is my new vector here. And I can write the norm of x, so let's do the squared norm, as, or actually, yeah, so what this is saying is that I can actually write x as the sum of, say, j equals 1 to d of some scalar alpha j times so uj. These are two separate things. I'm confusing a bit here, but okay, what's important here is this one on the right, that I can write x in this basis. Okay, so the fact I can always write it exactly in the basis, I can recover it as a scaled copy of each of these vectors here. And we will spend a lot of time thinking about this again, but I have the original basis, then I have u1 and u2, which are orthogonal. Okay, now I'm going to pick a value x, and it used to be I wrote it in the coordinate basis. This was x1, this is x2, right? The x and the y coordinates. But what I can also do is I can project it onto u1 and u2, and I can get this is alpha 1 and this is alpha 2. I can write x in the coordinate space of u1 and u2, basically. Okay, so it's probably a lot right now. I'm just previewing this. We're going to go over this again in so like a month. So if this interpretation of orthogonality is a bit kind of much, this is kind of a preview of it. And don't worry too much about this now. But okay, I want to show you, I'm going to give you a chance to ask some questions. I just wanted to review on Colab that, yeah, so anyways, so you can compute all of these things in very simply. Well, there are some things that'll be trickier, and we'll see how to do these sort of things later. But if I want to do a, yeah, we did transpose already. But if I want to do a the inverse of C, I just do, I have to use this linear algebra package kind of library inverse, and I can compute the inverse of C. So I have a matrix C, 1, 2, 3, 5. Compute the inverse, I get, this ends up being -5, 2, 3, and so -1. If I were to do C times its inverse, I should get back the identity matrix. And I don't do that exactly here. I get back instead the upper left corner is supposed to be a diagonal, 1, 0, 0, 1 is what I'm supposed to get here. Instead, I get something that looks pretty much like a 1, but it's got and these look like zeros, but it's actually the first 15 digits are zeros after the decimal, and then I get a 2. And the first 15 digits are 0, then I get a 4. So it's basically 0. There can be some rounding errors here. So you need to recognize that these are actually the identity. So there's some small so small discrepancies here that you should be aware of when doing some computation. Yeah, and if I try to do the inverse of A, which is not a square matrix, it's going to throw an error. Okay, it's not defined. Okay, all right. So that's all I want to show you. Okay. Now I'll take one quick question about the quiz, but then we should start and give you some quiet time to work on it. Or, all right, how about we just end it here, and then we'll, the quiz should be open in a minute. Again, I recommend you take it now. We'll be online on Zoom and also on in person to help answer any questions.
So can we actually find this or still use the theorem for all this?